one second. Overcurrent is any current in excess. All right, so any amperage that has gone over the rating current of the piece of equipment or the ampacity of the conductor. All right, it may result from an overload, a short circuit, or a ground fault. All right, so let's actually go over that a little bit. Now, anytime we have anything that is electrical, whether it's a light bulb, the outlet on the wall, a motor, a wire, connectors, the things that splice, the wire nuts that bring two wires together, even the little pieces of connectors that you put to make contact as your little contact point, anything that you can think of that goes with an electrical system has a current rating. Now, it also has a voltage rating, and it has a wattage that it's going to create once we get the product energizing. But for example, a wire rated at 15 amps means this wire can only hold 15 amps. A receptacle, like the ones that are on our walls, some of them are 15 amp rated, and some of them, the ones that have that little thing right here on the side, these will be 20 amp rated. Overcurrent happens anytime that device or that conductor experiences amperage more than the ones that it's rated for. Now, we have a lot of wires. We'll get into the wires, I think. Well, we're going to get into Article 110, and at the 110.14, we're going to explore this table, 310.16. All right, we'll get further into it. I think we went into a little bit of it yesterday, but we got a lot of wires. All those wires hold different amperages. So overcurrent can happen in one of three ways, right? There's three ways that they identified it in the definition. Just trying to head over to it. The first one is overload. All right, an overload happens very simple. An overload happens like this. At the end of this, and let me make them both the same now here on the bottom. All right, so I don't have a half 15, half 20. They don't make that. They don't make a half 15, half 20 amp receptacle. It's either 15 or it's a 20. But at the end of the line here, all the way back at the panel, I have a breaker, and this breaker has 15 amp rating. So as you notice, everything matches, and this wire here is going to be the wire that holds 15 amps. So you plug something into this outlet, that's 12 amps. So far, so good. But now you plug in something else to the bottom half of this receptacle, and this is going to operate at 10 amps. Remember, only when we turn it on. If you plug something in and it's in the off position, no amperage at all. Once you turn it on, now we have amperage. So on this conductor over here that's supposed to only be dealing with 15 amps, now it's dealing with 22 amps. All right, this is an overcurrent situation. Overcurrent is usually caused by plugging too many things into the circuit. Right? An easy one like that. There's other ways that this can happen, like a motor that when it's spinning operates at 12 amps, but then it gets jammed up by something, right? Let's say it's a conveyor moving some boxes, boxes get all stuck, motor can't turn anymore, it's struggling to keep turning, and now internally it's getting hotter and hotter and hotter as it keeps trying to turn. This is going to increase the amperage. This is another overload scenario. A short circuit and a ground fault happen when we have a different set of circumstances. Here's our load. Here's our neutral heading back to the panel. All right, this is our hot. Doesn't matter what voltage we're talking about here. This can be 120 in neutral. We can be talking about DC, positive on the hot side, negative on the negative side, or on the neutral side that I have here. This load has resistance. So as we send voltage into this side and we have resistance at the load, we have a circuit now. This is a circuit. The load is on, in the on position. We have amperage now being generated by that load, and this is what we call a closed circuit. You don't have to write that part down, but this next part is going to give you an understanding of what a short circuit is. A short circuit happens if I simply get rid of this load and connect the hot and the neutral together. All right, I'll design it another way. I'm going to keep the load here because usually we don't remove the load and just take the neutral and the hot and put them both together, but they come into contact in some way, and that's what a short circuit is. A short circuit is the hot and the neutral have come into contact with each other and have removed the load from the scenario. And not really the load, but they remove the resistance from the scenario. This is a short circuit. What happens in a short circuit is pretty intense. When this resistance here goes to 0, and we can run some numbers, since you guys just did Ohm's law, we can run a couple of numbers. And we can say, when we have, let's say, 120 volts, and we have, let's say, 0.01 resistance in this circuit, all right, we divide 120 by 0.01, and we're going to get 12,000 amps. In other words, when you remove this load from this circuit, or when you touch the hot and that neutral together, you have a runaway amperage effect. As the resistance in the circuit starts to drop and drop and drop and gets to 0 and beyond 0, I only stopped at 0.01, this can get even further, the amperage climbs in an equally proportional direction. Just like if voltage goes up, amperage goes down, or if voltage goes down, amperage goes up. We have the same effect when resistance goes away in a circuit. This is called an inrush of current. And it happens when we have a short circuit. There is a massive amount of amperage that comes into this circuit. It causes the breaker to trip instantly. More on this when you get into code D and troubleshooting, because we do go into these particular scenarios on how to identify when a breaker trips, if it's a short circuit or an overload or a ground fault. How do I know which of the three it is? But this is essentially what is happening. By the way, the same thing is happening in a ground fault when the hot and the ground come into contact with each other. Same thing, you're bypassing the resistance and you're touching neutral or ground straight with the hot. No more resistance, runaway amperage. Now, breakers are designed to handle this, all right? Well, not designed to handle 12,000 amps, but designed to respond to such a high inrush amount of amperage. They're designed to open when the circuit starts to see this immediate, and this happens instantaneously. There is no way to stop this. That's why a short circuit will have massive arcing, and depending on the voltage, this number gets way higher. A short circuit on a 120 volt circuit, 12,000 amps seems like a lot. Not as much as if the voltage here was 480 volts, what comes in standard to an industrial building. Now we have 48,000 volts. And imagine now a short circuit on the utility lines outside. That could potentially be 12,000 volts. Now we have 120,000 amps. This is why if you ever watch those videos on Instagram or social media or wherever where you see like a short circuit on a power line and it's just a massive explosion, that's why this massive amount of amperage just rushed into this circuit. And it can potentially cause fires and everything. If breakers and fuses don't trip, fires happen along the way. So all of this, too much amperage being plugged into the outlet, or a short circuit or a ground fault causing this massive inrush of amperage or inrush of current, now to go back to the definition, falls under the umbrella of overcurrent. So just take note of that. overcurrent is not an overload or a short circuit or a ground fault in particular. It's all three of them. And it's a little bit confusing because there's this word here, overload and overcurrent. So an overload is an overcurrent, but a short circuit and a ground fault is not an overload. It's an overcurrent. Be careful with that because that's an easy place to ask a question right out of. All right, any follow-up questions to the short circuit, ground fault, or overload? Again, all three of them are considered too much amperage in the circuit, and that's why they get that word definition of overcurrent. All right, down to the Q's. Qualified personnel. You guys can imagine what a qualified personnel is. One day, you guys, that'll be a qualified personnel. Sorry about that. I went a little too far here. Missed the Q's. Oh, there it is. Just like one Q. There it is. Couldn't find it. Qualified personnel, one who has skills and knowledge relatable to construction and operation of the electrical equipment. I don't think there's anything more to say about that one. Just make sure you have it highlighted. Next one is right under that one, which is raceway. Raceway is going to come in a lot of different forms, from Romex that you're working with in code A to the conduits that you'll be bending in code D and also in code A with EMT. In code D, you might get into RMC. I think they're changing that around a little bit. But also the flexible, Romex, the ones we bend, EMT, things that have cables inside, wires inside, even bus bars, these larger pieces of metal that connect circuits together, those will be inside panels. But a raceway, just to find that definition, is really just right here, in that right there, an enclosed channel. All right, emphasis on the word enclosed. All right, so if you have, for example, wires laying on something that are sort of protecting it from people getting near it, but the wires are exposed in some way, this is not considered a raceway. Raceway would be a conduit or something where the wires are tucked away inside, or again, to use the word they're using, enclosed. Channel designed expressly for holding wires, cables, or bus bars, with additional functions as permitted in this code. All right, now they do have a few extra ones here. We're not going to really get into those, but you can see there are communication raceways, for example, things for like fiber optics or data communications for the internet, for any kind of data communication system, satellite systems, fire alarms. There's all kinds of things that can be considered a raceway. In fact, here in the communications raceway, there is an odd one, which is this right here, that word. Fire alarm cables in plenum. All right, plenum is the area right above you guys in that classroom. All right, right above you in that classroom where those ceiling tiles are. If you open up that ceiling tile, that area there, before it actually gets to the actual roof of the building, all right, you have a ceiling tile and you pop that little ceiling tile up. There is concrete, probably about 2 or 3 feet away from those ceiling tiles. Those ceiling tiles are hanging on these little wires that are holding up that whole ceiling grid. So when you pop this up, that area right here, between the drop ceiling and the actual concrete of the building, is called plenum. All right, and that area there is considered a raceway for communication cables. All right, now, if this was my course, I would have you guys highlight that. In fact, I'd just go ahead and highlight it now. You are going to get into communication later on. This would be one that I would want students to know about just because of that plenum area and some specific low voltage wiring that goes in there. So I don't know if Mr. Aaron would want this highlighted or if a question is going to come up from him, but I would say, just in my opinion, highlight this because low voltage communications is going to come up in a few modules. So now you have kind of an understanding of where these wires get ran. Low voltage stuff can be in those areas without conduits. without like being in a piece of EMT or any kind of flexible conduit, because that ceiling area is considered a raceway in and of itself. So a lot of different types of raceways, but the most common ones are going to be the conduit type. All right, next question, and here I almost want to, or sorry, not next question, next definition. There's two to really unpack here. So the word is receptacle, all right, which has a definition here, and then we have receptacle outlet, which has the definition that I would more likely say you'll deal with. All right, but let's read the first one. It says a contact device installed at the outlet for the connection of an attachment plug or for the direct connection of an electrical utilization equipment. Remember, utilization equipment is something like an air conditioner, designed to mate with the corresponding contact device. All right, a single receptacle is a single contact device with no other contacted device on the same yoke or strap. A multiple receptacle is two or more contact devices on the same yoke or strap. So just want to make sure everybody's got all of those words understood. All right, we have receptacles that are devices where we have a little single yoke with one single outlet. All right, and this would be considered just exactly what that is. A single plex is technically the right word here. It's called a single plex. All right, this is considered a single receptacle, a single contact device with no other contact devices on the same yoke. That little piece of metal that we have the little screw on that we screw into the box itself, that's called the yoke. All right, Y-O-K-E, not L-K like the egg. The more common one, I don't even know if you guys have seen one of these, in particular a single. The more common one is the duplex receptacle that we call it. Still only one yoke, right? It's still only one yoke. But this is what they would consider the last sentence there. A multiple receptacle is two or more. All right, they do have 3 of these sometimes, and they have 4, and you can actually get them in, like you can order them online with more. You can have 6 or whatever amount. I'm not sure if there's a limit, but I have seen some longer versions of these just for particular sound equipment and in certain areas. But a multiple receptacle is 2 or more, like I have there. The most common is this one. Contacted devices on the same yoke. All right, so on the same yoke itself. So the yoke, the piece of metal, switches have a yoke as well, but here they're talking about a receptacle. All right, so receptacle outlet would simply just be kind of a follow-up to that last bit right there. An outlet where 1 or more receptacles are installed. All right, so there is actually a technical thing going on here where they're saying the receptacle is a device that is installed into an outlet. The outlet being the box that would be on the wall waiting for the receptacle to go in there. The other definition, receptacle outlet, is the box on the wall that will receive the receptacle, right? Almost same, but one is going into the other one, all right? A receptacle outlet is only specifically designed, as it says here, for an outlet where 1 or more receptacles are installed. Going back to the definition of receptacle, a contact device installed at an outlet. All right, sometimes a little bit confusing. Again, it is a law book, so they do have to make sure they're ironing out any which way this can get twisted and someone can try to get away with something. All right, let's head down to SW for switch. By the way, again, as always, any follow-up questions to any of that. But we are just on definitions, so I'm going to assume no follow-ups just yet. All right, so here again, switches have a couple of different definitions, but we're only going to focus on one general use switch. This kind of is the cover-all, or, umbrella term for all of these. A switch intended for use in general distribution of branch circuits. It is rated in amps, and it is capable of interrupting its rated circuit at its rated voltage. All right, there are some other types of switches. Isolating switches, switches for motors. Even when you come down here a little bit, sorry about that, we have disconnecting switches, interrupting switches. All right, there's a lot of switches in the electrical world. When you get into the motor world, even more. There's sensors that are considered switches, things that. But here's what I want you to know about switches, just to go back over to that definition, because it is a little bit extra than it needs to be. All right. First of all, a general use switch is one intended for general distribution and branch circuits, meaning inside of a house, inside of a building, just intended to turn on and off lights. All right, now on and off lights is generally what we're using switches for. Back in the day, some homes used to have a switch on the wall that controlled an outlet, for example, so there are those as well, but that would still be considered a branch circuit. It is rated in amps. Remember what I said, everything electrical, no matter what it is gonna have an amp rating. And it is capable of interrupting. What do they mean by interrupting? Draw a symbol for a switch here. This is the extra thing I want you to understand about a switch. So, when we talk about, in fact, let me get rid of that for 1 second. When we talk about switching, yes, if you were just, at a house with a switch, someone would tell you turn on the lights, or someone would say, hey, turn off the lights. But to understand that on a little deeper level, because not all switches are turning something on, sometimes a switch can start a motor, sometimes a switch can simply provide electricity to a heating element that's heating up, so it's not actually turning on. So the use of the word on and off is not really good. But I am going to put it over here just to start the conversation on what we mean. The way I want you to understand switches on a little bit deeper level would be the open and closed. All right? If something is on, that means the switch is closed. If something is off, that means the switch is open. All right, and we can even go further into this, where this would be starting and this would be stopping. And by the time you get into PLC and all of that stuff, you'd get into binary, where this would be ones and zeros. So this is why I say understand switches on a little bit of a deeper level, because as you go through the modules, you're going to experience or come into switching in different types of scenarios. There's one more that's added to this when you guys get to PLC, which is true-false, but we don't have to get that far down the line. For anybody who's done electronics, you may have recognized that term. True is closed, false is open. So that's how you want to understand a switch, whether the switch is open or whether the switch is in the closed position. And then, of course, the resulting effect of that, which hopefully seems obvious, meaning that if the switch is closed, then voltage or current, this is why I was telling you guys, the books will say current is flowing, but I always like to remind electricians that it's voltage that we're measuring. So current flows when the switch is closed, or voltage flows when the switch is closed. Both are fine. If the switch were open, then we would not expect voltage to be on the other side of the switch or at whatever load this is. So this is already something to just put in your brains for when you guys get to troubleshooting. If something is not on, the first thing I want to do is measure power at the thing that's not on. I want to measure to see if there's voltage. If there isn't voltage here, then I'm going down the line of this circuit looking for something that has opened. If there is voltage here at the load, then everything down the line is closed. Voltage got to the load correctly. The load is not on. The problem is now the load. So it's a way to also understand how to troubleshoot these circuits, and these circuits will get more complicated as you guys go into motor control and PLC. I knew switch was going to need a little bit of, because I did want to get into stuff like this. So like I said, this is how you want to understand switches now. Forget on and off, put that aside. that's for the average individual. Now, there's going to be a bunch of different types of switches. As I said, all of them, in principle, work in the same way. They open, they close. They send electricity down the line to the load, or they open and no more electricity down the line to the load. Some switches will be single pole switches. One open, one closed, that's it. Some of them will be two pole switches, providing 240 volt to a circuit. Some of them will be three pole switches, providing 3 phases to loads like motors and etc. So different types of switches, concept remains the same. They're either open or they're closed. And really that's what anything in electrical can be. It's either an open circuit or a closed circuit, can't be halfway. All right, any follow-ups there on switching? I'm going to keep asking. Somebody's going to have a question at some point. All right, let's go over to ungrounded. Ungrounded. All right, now, this is a really, again, sometimes they just go in excess of what they need to explain. Ungrounded, not connected to ground or to a conductive body that extends the ground connection. So there's a few ways that you can look at what they mean by this, because we have words for the hot, neutral, and the ground. All right, the hot conductor, the one that has the spice on it, right? This is the one we call ungrounded. This is the ungrounded conductor because fits the definition. Not connected to the ground or to a conductive body that extends the ground. What is a conductive body that extends the ground? Well, a metal box. A metal box with a little ground pigtail on it and a conduit running a ground to this box. Right? All of this metal is conductive body that extends the ground connection. So anything that's ungrounded is not connected to anything that is grounded. Right? Very easy to break that down. So we like to call the neutral the grounded conductor because it is grounded to the system itself. And we like to call the ground the grounding conductor. All right, big reminder, this does come up in literally every module except for the motors or the industrial courses. We kind of get away from this or by that point. But that's what you should be understanding these particular wires as. The hot is the ungrounded, the neutral is the grounded, and the ground is the grounding. All right, the ground creates the system, ing, grounding everybody. The neutral is grounded to that. All right, so it is connected to that ground. And then the hot has nothing to do with them. And if they do, hot and neutral come into contact, or hot and ground come into contact, right? Short circuit, runaway, amperage, explosions. So that's why it's ungrounded, can't touch the ground. All right, so the definition that they have here, I would say, is a little bit vague just in terms of what are they talking about in general, but they just simply mean anything that is not connected to the grounding system. All right, the next one, which you guys should have already talked a little bit about in the last module, which is voltage. This is the code book, so they are being a little bit more specific as to what they mean. So we'll just have to highlight the first one. Now, actually, we're gonna highlight a couple more, and I'll bring them to your attention because there is a little bit more to unpack with voltage. Again, this is a code book focused on electrical construction, so they do have a more concise way of explaining it to us. Because the first definition here, as you're looking at it, of a circuit, the greatest root means square, or RMS, difference of potential between any two conductors of the circuit concerned. That's what the physics definition of voltage is. The physics definition of voltage is that exact thing. Or sometimes we call it true RMS. It's the peak point on the sine wave. That's peak RMS. All right, because the entire sine wave, let's just take one phase, is RMS. All right, so this is a way to measure the voltage as it's going between positive and negative. This peak point here would be peak RMS. Usually that is also called true RMS, because that is when I go to measure an outlet. Remember, this is happening 60 times per second that this thing is going up and down between one cycle, right? 60 cycles per second or 60 hertz per second. And that's just what it shows up at. We do have pieces of equipment that can increase that hertz up to the 300s. So that's the definition of voltage in the physics sense, but here's the other ones that I want you to make sure you understand, because as electricians, these are the ones that concern us. The first one is down here, which is high voltage. Now, high voltage, again, this is all depends on what world you work in. If you work for the power company, then high voltage could be 100,000 volts. If you work in the world of electronics, high voltage could be 5 volts. But for us, in the code book and for general electrical concerns, high voltage is a potential difference of more than 1,000 volts. All right, so make sure you have that highlighted. All right, high voltage more than 1,000 volts. All right, we do have the counterpart. All right, if there's one, there's the other, which is low voltage. And this would be rated 24 volts nominal or less. So voltage less than 24 volts. And now the most important one would be this one. The voltages that you will likely be working with, there's one very important one that's not there. I do not know why it's not there, but I'm going to give it to you over here in a second. But just to read this, a nominal value assigned to a circuit or system for the purpose of conveniently designating its voltage or class. So this is in general, and the word nominal means in theory only. So we have 3 voltages or 3 voltage systems that we work with, 120 and 240. This is what you're going to find in residential. All right, we have 270. I'm writing the small number first. I know they have 480 first, but I'm putting 277 first and 480. This is what you find in industrial. There is one more. It's actually the one that's very, very common for commercial buildings. In fact, the building that you guys are in right now has this voltage, which is 120, 208. Oops, sorry about that. Hey, one more. There we go. And this is usually found mostly only in commercial. However, sometimes industrial will use it. The only problem with industrial using it is if you have a lot of motors, right, if you have a lot of large pieces of utilization equipment or machinery or motors in general, you want to operate these things at the highest voltage you possibly can give them, because voltage goes up, amperage goes down. So if I give this motor 480, then the amperage that the motor generates is going to be lower than if I were to energize this motor at 208. The motor is fine with either voltage that you give it. The panel that this motor is being fed from would be happier if the amperage were less, because now I can put more motors per panel. So this is why industrial locations like a high voltage coming into it. In fact, there are some that are even higher than that. If you'll notice, there is 600 volts here as well. There's a 600 volt also, which they don't have it here, but the counterpart to 600 volts is 347 and 600, and this would be absolutely only industrial. These are called nominal voltages, all right? As it says here, conveniently designated for the purpose of. For the purpose of what? Well, when I have to do calculations. Right, if I want to do Ohm's law, I need a voltage number that we're working with. You can say, all right, well, go measure the voltage. Well, what if I'm doing Ohm's law in a building that doesn't exist yet? We're still in the process of design. I can't go measure anything. So I have to use some kind of established number. And so there is where the word nominal will come in. All right, this will have some other places where this will show up as well. All right, in worlds like wattage and VA and all this good stuff, especially wattage. Wattage has this little issue as well, because there's wattage estimated that's going to happen when the thing is on or when the load is on, and then there's wattage measured, the one that is actually taking place when the thing is energized. And why would the wattage change? Well, because the expected wattage was calculated using a nominal voltage. But when we actually plugged the load into the outlet, well, the outlet didn't have 120 perfectly there. It might have had 122, 123. It could have had 119, 118, 115. So these little fluctuation in voltages are common throughout all voltages. In fact, you guys can try that now with the meters that you have. Turn them over to voltage and start to plug them into outlets, and you'll see the numbers are not 120. Now, can they be? Sure, but it's very unlikely in most cases. So it's an Ohm's law thing. If I divide wattage over 120, I'm going to get a specific amperage, or power. I shouldn't say wattage when we're talking Ohm's law, but that's what it is. If you make that 120 115, that's a different number for amps. It just is. So the real happens when you actually connect stuff to a load. The calculated happens when we use, again, these nominal voltages. So get familiar with these nominal voltages. Let me just go ahead and erase this last one as far as get familiar with. Don't worry about the 600 one. But these three systems you should, in practice, start to get very familiar with. All right, 120, 240, that's in every residential. So that's usually where we start as a course teaching more focused on residential. And then we start to expand a little bit. These two are three-phase systems, which are quite different from that one there, which is a single-phase system. All right, we're almost out of definitions. One last thing to point out, which is watertight or weatherproof. And it's the same for both of these, except it has sometimes a different way of showing up in application. So watertight is the constructed so that moisture will not enter the enclosure. And then waterproof is so that exposure to the weather will not interfere with the operation of whatever you've plugged into this. So for example, you can have a watertight box that doesn't allow moisture to get into the box. But for example, if you had that box, right, you have your watertight box here, and you had an outlet here, and you put this outside, sure, the rain's not getting into the box because the box is watertight, but the outlet is getting all that water all over it. So it could, in a sense, not always, I've seen these things get rained on all day, but you'd be surprised. But it could, in a sense, as it says there, interfere with the successful operation of whatever you have plugged into this. Whereas waterproof, that's a little bit different. This is going to have a cover, for example, like the one, you've probably seen it before, a cover like this one right here, that has a complete structure all the way around here. I'll put it up a little closer, all the way around the outlet. Now, it can rain all day, and this is waterproof, right? You can see by the top right here where it says waterproof cover. All right, so we have rain-tight junction boxes, and I'll show you a rain-tight junction box. Let's go with that. All right, rain-tight electrical should be good. All right, yeah, I guess I can use that one. And this would be considered a rain-tight box right here. It would have a cover over it, and it has an ability to seal off all of those little holes that it has here with threads. You see all those little holes have threads on them. So it does seal this up completely. But if you were to mount an outlet just wide open on one of these boxes here, the outlet would not be waterproof. So you have to have a waterproof cover for it. So waterproof, rain tight, two slightly different set of conditions. But in most cases, they're both kind of used together. There is an informational note for this one as well. It says rainproof, rain tight, or watertight equipment can't fulfill the requirements. Not in all cases, but I would say in most cases where you have all these conditions. All right, snow, ice, dust, temperature extremes. Some of these are not a factor, as it says there. All right, that wraps us up with our definitions. All right, so again, if there's any follow-up to any of these, feel free to send me an email if you have any other questions in it. Also, send me an email, or you can bring it up in class in the morning, not in the morning, but when we first get into class, you can bring up questions. Like if, for example, you read another word in there, or you work with something and you looked it up, and you looked it up in one of the definitions, and you're like, hey, this component, kind of want to know what this is. Always feel free to reach out and let me know if you have any follow-ups to anything. All right, good. Now we can jump over into the next article, which is going to be Article 110. All right, Article 110, you're going to find that on page 63 of the code book. And now we start to get into general requirements for electrical installations. Now, these all kind of 90, 100, or I should say 90, and a lot of the definitions that we've talked about in 100 are kind of going to roll over into this article as well, because this article is about the general requirements for electrical installations, which we've been looking at a lot of these requirements in some ways. All right, so these are the articles that we're going to be looking at out of this code book, or sorry, out of this particular article. Article 110.2 approval. All right, 110.3 examinations. 4 voltages, 5 conductors, 6 conductor sizing. We do make a nice little jump into execution of work and into electrical connections at 14. Now, hopefully we can get all the way into electrical connections and at least end there. That way, tomorrow we can start on unpacking that a little bit, because it takes us into a completely different code section. I think we can get there. I don't think there's anything here in the beginning that really needs too much of a breakdown, because again, we've done already a lot of explaining. For example, let's start here with 110.2 approval. Now, as I have pointed out, things have to be labeled, things have to be listed. You can find it here in the informational note. Use of equipment, see definitions for approved, identified, labeled, and listed. There is our word. Approval, the conductors and equipment, the wires and all of the equipment. And just by the way, when they say equipment here, they mean everything. All right, they separate wires from everything. They can almost throw wires into equipment, but they do separate that. So wires and everything else required or permitted by this code book shall be acceptable only if approved. Approved by what? Well, approved by what we've talked about. Listings, testing facilities, people that put motors to the test, that run the light bulbs. If the light bulb says, it has X amount of life on the light bulb, then it's been tested for that. If it says that it generates, 5, 10, 15, 20 watts, then it's been tested for that. All right. If it says that you can connect 120 volts for it, it's because it's been tested at 120 volts and it has held. All right, nothing, no damage to it. You buy something that hasn't been tested, it says 120, and this is where people have these fires in their houses out of nowhere from things. I actually bought something like that, and I use it, but I don't really like it. Like my headboard on the bed has the USB plugs, and it has an outlet plug. All right, you plug that little box straight into an outlet, and this is the first thing that I thought about when I was assembling this, because it was made somewhere else. And I was like, this thing is not UL approved. And this is one of those things that could cause fires, because if I plug something in here and, it's generating a little bit too much amperage, this piece of plastic that's on this bed frame that's probably not been tested could potentially melt, catch fire, and all that stuff. All right, so I have something that I use which is probably not tested. I don't know if it's not tested. I didn't actually look inside of it, but it came from elsewhere, so I don't think it was. All right, the next one, same thing. It kind of all falls within the next, within the same overall. Things have to be labeled, examinated, identified. So examination, which is 110.3, identification, installation, use, and again listing, product certification of equipment. In judging equipment, considerations such as the following shall be evaluated and suitable for the installation and use in conformity with this code. Literally all you have to highlight for this. All right, for 110.3, that is the note. Whatever it is that we install, use, as it says there, equipment considerations such as the following. Number one, suitable for the installation and use with conformity to this code. And that's how they put a stop to anything that isn't properly listed. Now they go into a bunch of other ones. We don't have to highlight those. Keep in mind that questions can come out of it. When I tell you to highlight something, it doesn't mean a question and only this thing that we've highlighted is going to have a question from it. It just is the most important thing of the article that I want you to know about. But a question can be asked from the other one, so just keep that in mind. Mechanical strength and durability, wire bending and connection space, electrical installation, arcing effects, right? We have arc fault protection devices for that. They should be listed and tested for all that as they go and get installed, right? Sold and installed. So let's jump down into 110.4, which is voltages. All right, voltages. The voltage considered, and I'll wait for everybody to get there, sorry about that, 64. The voltage considered shall be that at which the circuit operates. The voltage rating of electrical equipment shall not, remember again what shall not means, absolutely cannot change this, shall not be less than, in other words, minimum, than the nominal voltage of a circuit to which it is connected. All right, so again, the voltage rating, what this piece of equipment is rated for, 120, 240, 480, 277, it is rated for that. That rating of that piece of electrical equipment will not be less than the voltage that you are about to connect to this thing. And people do make these mistakes. All right, people make these mistakes all the time, especially with outlets that you're buying. These outlets, as I pointed out earlier, can have different voltages. All right, so you can have an outlet that has 240 volt rating, an outlet that has 120 volt rating. You're going to install an outlet in a 240 volt rated circuit, and you've bought an outlet rated for 120, and now you're violating that particular code section here. I would say there are a few products that this comes, switches as well. When we buy switches, it's also something that we have to keep in mind anytime we buy anything. This, I was going to say, more so falls when you get into the world of fuses, when you start to get into industrial fuses, because fuses are one of those where there's two types of ratings for fuses. You either buy fuses rated for 250 volts or less, or you buy fuses rated for 600 volts or less. So that big separation there can mean somebody's installing a fuse that will fit into the position, but on a higher voltage system. So this will, again, this will follow you around in some other areas, but just keep that in mind. Whatever piece of equipment that we install into a circuit has to match the voltage that the circuit is about to give it, or has to be rated, I should say, for the circuit that you're about to plug into it. All right, the next one's right before it. The next one after that is right before that one as well. And this is going to start to take us into that next table that I mentioned, which now we're going to get into conductors, right? The wires. Conductors, 110.5. All right, make sure you highlight that one, and 6 as well. Conductors used to carry amperage current shall be of, and this is the only type we can use, copper, aluminum, or copper-clad aluminum. which is basically aluminum with a little coating of copper, unless otherwise approved by this code. There are some things, of course, that can take fiber optics cables, but fiber optics not being copper or aluminum, it's actually glass and plastic. So there are other things, sometimes silver or gold for sound system and electronic equipment. But in most cases that I'm aware of, everything is copper or aluminum. And these days, everything is generally copper for most of our work. All right, so conductors must be, like I said, copper, aluminum, or copper clad unless otherwise mentioned in the code. If the conductor material is not specified, the sizes given in this code shall apply to copper conductors. So in other words, if I'm about to size some wires for a piece of equipment that we're energizing, I make all of my calculations using copper in mind. All right, and when we get to the table 31016, we'll get to it in a little bit if we can get to 11014, which just looking at the time, it's 613 maybe. This table is going to separate in half copper and aluminum clad. So if I don't know what we're connecting to this, like I don't know if the building people that we're bringing this piece of equipment to are going to want aluminum wires, they can ask for aluminum wires. Or for whatever case, aluminum is going to be used, but I don't know that. I make all of my calculations going with the amperage of that table that I said that on the copper side. So unless we know that another type of material is going to be used, as it says here, the size given in this code shall apply to copper. If other materials are used, the size shall be changed accordingly, but then we know other materials are used. All right, the next one, 110.6, conductor sizes. And the only thing you have to know here is this. AWG means American wire gauge. Now, all wires are assigned a size to the wire. All right, that's going to come up further down the line. We're not going to be exploring that right now. Right now, we're simply going to be exploring the wires and going through the sizes based off of the AWG, the American wire gauge of the wire. As I had said before a few days ago, I think, I was mentioning, again, I'm teaching a lot of classes right now, so I think I may have mentioned this to you guys where wires are sized. Yeah, I think we went over this yesterday. Wires are sized in gauges. The thickness of the wire is given a gauge, just like any piece of metal, like sheet metal, is given a gauge based off of how thick the metal is. And so wire is the same thing. Now, who determines wire sizing is, again, the American wire gauge system. It's a system that just assigns different sizes a number to those sizes. So number 12 wire, number 14, number 10, number 8, all of this was assigned an American wire gauge number to just give the wire a way to, be selected versus another one. Okay, so we've got these out of the way. Voltages, conductors, conductor sizes. We're not going to worry about wire integrity. We're jumping over to 12, just to make sure where 12 is right here. Mechanical execution of work, which is, we're only going to highlight two things from here. One, which is electrical equipment shall be installed in a professional and skillful manner. This is one of those where it's interesting because this gives power to the inspector to say, I don't like how that looks, remove it. Which is usually not a thing that they should be concerned with, because the looks how I did something, for example, if I ran a conduit along a wall and I didn't run it level, right? I ran it off level. It doesn't look good. If they want that to go because it just looks terrible, then they can tell you to remove it. All right, if you install a panel and the panel is slightly leaning, all right, this is a lot leaning, but if it's slightly off, they can make you remove it and level it and make it better. All right, which is, again, almost something that the inspector should not care about, because if it's a little bit off level or if my conduit is not level, like, what do you care? You know, the wires are safe in there, the conduit is installed safely, it's not coming off the wall. Okay, so it's a little off level. What's the big deal? It's still secure, it's still not going anywhere. A hurricane can pass by here, it's not going anywhere. But this again, because it's a law book and an inspector might go, hey, get that off the wall, and you might say, you don't have authority to do that. It looks fine to me, but they can just point to this one code and say, I don't think it has been installed in a professional or skillful manner. And Article 90 pretty much gives the inspector all authority in contemplating, right? It says contemplate. So they're allowed to just have a thought and say that thought is what we're going with. So, all right, number one, skillful and professional manner. And then number two is A. This is the only other one I want you to make sure you highlight, which is unused openings other than those intended for the operation of equipment. Those intended for mounting, like you guys are bringing Romex into a junction box, you are bringing Romex into a panel, you are bringing wires into a panel. Or those permitted as part of the design for listing. In other words, any little opening on a piece of electrical equipment shall be closed. All right, to afford protection, sustainability, substantially equivalent to the wall of the equipment. So specifically with our electrical junction boxes, all right, this happens a lot, and this happens a lot too on panels. All right, because on panels, especially on panels, when you're in an electrical room and we're bringing a lot of conduits to these panels, all right, and conduits are being brought into the panel, and somebody's running a conduit here, and they estimated that when they turned to 90, they were going to go into that position of the panel. But when they turned to 90, they didn't get that done so good, and they're going to be a little bit higher. So now they just choose the little hole one above on the panel. But now they've already knocked this one out. So now there's a hole there where there's no conduit in that one, and you're not allowed to turn over a job like that. All right, you're not allowed to say, we're done, walking away, power's on, everything is complete. So they sell these little KO seals, they're called, or knockout seals. That pretty much, and there's a bunch of different types, right? So here we can look at a bunch of different types. This is one very common that snaps right in. All right, they have different sizes for different conduits. They have the rain tight ones. This is what the rain tight ones look like, where they have that little screw. I had pointed out that the rain tight comes in threaded. So these are those little threaded knockouts, or KOs, we'll call them as well, that will go into one of the holes in the boxes, right? You can see this being used right here between those two holes. And they snap right in. They're actually a little bit loose when you put them in, but that's the idea. All right. Now you can get away with this sometimes if there's a junction box and then there's drywall over it, and the inspector doesn't see it anymore. But this is why inspections happen all phases of the job, before the drywall has been put on the walls and before we start to seal things up or seal the walls up. The inspector does come out and take a look at everything. And make sure things like that have been taken care of, right? So knockouts, and also they're looking for things properly supported, etc. So this is what that next part is saying. Where metallic plugs, those are the plugs that I showed you, or plates, they also make plates that can go around the hole if the hole is gigantic, are used with non-metallic enclosures. So in other words, you're putting a metal plug on a plastic, non-metallic enclosure. They shall be recessed at 1/4 of an inch. So it's just giving you a way to install it at that point. But the main thing out of that section that I wanted to make sure, two things. Again, everything has to be installed in a professional and skillful manner, and any unused openings on electrical equipment shall be closed. All right, now let's jump over to 110.14, which is electrical connections. All right, that's going to be up there on 65, top left. All right, so I'm going to read a little bit of this, and then we'll start to get into the stuff that's going to be important. But as it says, because of different characteristics of dissimilar metals, that just means metals that aren't the same, like copper. You're splicing, let's say, for example, copper to aluminum, which you can. Devices such as pressure terminals or pressure splicing connectors and other soldering lugs shall be identified for the material of the conductor. All right, now I'm going to skip a little bit ahead and go down to terminals. All right, and we'll read terminals, and then we'll come and tie those two back together. Connection of conductors to terminal parts shall ensure a mechanically secure electrical connection without damaging the conductors and shall be made by means of pressure connectors, which we just read about. Solder lugs. Soldering is melting, which we should never do in certain circumstances, but for large conductors, sometimes they do solder into certain pieces of equipment. Or splices, which is normally the way we're putting two wires together, is we're splicing them together to flexible leads. Connections by means of wire binding, screws or studs, and nuts, which is usually what we're using, wire nuts, that have upturned lugs or the equivalent shall be permitted for 10 or smaller. We can ignore that last part. I'm going to read splicing and then we'll end it right here. This will be the important part for all of what I've just read. Splices. Conductors shall be spliced or joined with a splicing device identified for the use or by welding, brazing, and all these other means. I'm jumping down to the end of that paragraph. All splices and joints and the free ends of the conductors shall be covered with an insulation equivalent to the conductors and identified insulating devices. And now let's jump to the last one, and then we're going to break all of this down a little bit. Temperature limitations. The temperature rating associated with the ampacity of a conductor shall be selected and coordinated so as not to exceed the lowest temperature of the connected termination, conductors, or devices. All right, conductors with a temperature rating higher than specified for the termination shall be permitted. So all of that is concerned with two things. One, everything that brings two wires together. And there was a few things that they were talking about there. We could solder them and this, that, and the other. More likely, we're using a wire nut cap, right? I'll just choose the red one, where we bring a wire in and we bring another wire in. We twist these wires together, and they are now spliced together. But there are other ways that you can do that as well. You can have a connector that gets crimped down onto that wire, that gets compressed down onto that wire, and you've probably seen these that have a little channel that looks like this. And then you can screw this down into a termination point. All of these things that bring two wires together or join wires to a termination point have to have a temperature rating, a heat rating, that is the same as the wire's heat rating for the insulation wrapped around the wire. All right, now we'll just let that fact be a fact, and now we're going to jump over to the table that I had mentioned. So all the terminations, anywhere where you bring a wire in, the outlet, all right, the side of an outlet, here's our outlet, the little side where we have the screw, that screw right there that you're about to terminate a wire to has a temperature rating. And that temperature rating has to match the one on the wire. Or the wire can be greater than that, but in no case shall the wire's temperature rating be less than whatever termination point rating that we're going into. Okay, now we have, I don't want to take too long because we do have a teacher coming in. We do have 3 minutes, so I do want to head over to this table. It is 3:10:16, and we'll end it here. All All right, and here's where we'll start tomorrow at this table. There's more to unpack, but I just want to show you that first part about the temperature. Let me jump ahead here and find the specific table. I'm not mistaken, it's in, one second, I have it here, page 187 of the code book. All right, 187. 187. All right. So hopefully everybody is finding their way to this page. It looks like this. And this is technically not article. All right, this is not article 3.10.16. This is table. Table 3.10.16. There's a lot of tables in the code book. All right, this one happens to be table 3.10.16. So that is something that the tables will have. They'll all be given like a code number as well. And let's read what this table says. Ampacities. Remember what ampacities was? The amperage rating of insulated conductors. Now, we'll unpack this a little bit more because they are telling us there is a caveat to this. There is a qualifying factor to these ampacities, which is no more than 3 current carrying wires in a raceway. So if you have 4, 5, 6, 7, 8 wires, things do change, but we'll explore that a little bit more. But to the point that I want to show you, first of all, copper, aluminum, 2 sides, different sides. All of these little abbreviations here, all of these are insulation types. All right, these little insulation types mean things like some of these insulations are rated for very high heat. That is where you see the TH, thermo heat. All right, some of these are for wet location. This is where you see these W's. All right, some of these are rated for oil and chemicals and etc. So these insulations do protect the copper inside the wire. But here is the temperature ratings up top. All right, there's 3 types of temperature ratings. Usually we go with the Celsius, even though in America we do Fahrenheit for everything. But for the insulation types, and I think it's just because it's easier numbers to remember. I think somebody just kicked this off and no one ever changed it. But we go with 60, 75, and 90. And also the code sections will reference the Celsius. So, in other words, now going back to those sections that we read, the termination points have to match, or rather I should say, the wires have to match the termination points and not be less than the rating of the termination point. All right? For example, if the termination point says it has a temperature rating, and they will all only have one of these 3. If the termination point says it has a temperature rating of 75 degrees Celsius, then we need to pick a wire from the 75 degrees Celsius category or the 90, not the 60. All right, so that would be violating the temperature rating of the termination point or things where wires are spliced. That was what all 3 of those sections, or 4, I think it was 4 of them, were telling us. If you're bringing 2 wires together, the heat rating of the thing that is about to connect these 2 wires together has to be factored in when you select the insulation type for the wire being connected. All right, it's 6:31. That's a good time. We have till about 6:40, but I'm going to start to wrap these up right at this time just to make